Then let's start. I will go back here. The work I present today is my PhD work with ZF Mobility Solutions at ZF Mobility Solutions, together with the University of Erlangen-Nuremberg, the chair of Professor Germann and Kai Steffen Hirscher is my mentor there. And yeah, I'm doing performance evaluation of hill systems with network calculus, and the actual paper will be published at the IEEE conference, ICE CCME. And yeah, now let's go into the details. Hardware in the loop simulation, yeah, what is it? It is an enabler of product validation for complex technical systems. So like the autonomous transport system we're actually developing here at ZF. And it has not been a system under study before, so it's mainly used for validation of technical systems like ECUs and so on. But what we are doing is building up these test systems and try to give guarantees about their behavior. And their the hill means hardware in the loop simulation means that we have to ensure strict real time at the interfaces to the device under test, and high data integrity. So the technical concept for open loop data re-injection, what is one mode of hardware in the loop simulation beneath the closed loop simulation, is to use a playback buffer. And yeah, there are no buffer over and underflows are allowed. That's why the KPIs are the minimum needed delay and the maximum backlog in the system. And the proposal for the performance evaluation approach is based on measurements, then network calculus for streaming systems, and discrete event simulation. Here you see an overview of the interconnection of the different methods. So we use measurements from the hill system itself. These measurements are used directly for trace-driven simulation, or with distribution fitting or advanced distribution fitting for the input modeling of the discrete event simulation model we developed. And the measurements are also used for arrival and service curve approximations to calculate with network calculus the buffer and delay bounds, and also the needed pre-buffer delay to use it as a parameter in the discrete event simulation model. And the bounds are verified by the simulation model. And with the simulation model, we can change the workload, like cycle time or payload of the streams, and generate workload near the system bottleneck. So here you see an overview, a really easy model, conceptual model of the hill system. It consists of a host computer, which controls the hardware in the loop computer, and which is a real-time PC, and they are both connected via Ethernet. Then the hill computer is connected with real-time communication interfaces to the device under test, but the real-time communication interface and the device under test are not scope of that study. We assume that they work in real time. We look deeper in the hill computer itself, and therefore I propose that detailed model here. Let's go through the model with the signal chain. So we have a connection to cloud or to a storage system. From there, we copy the data locally to the RAM disk, and with the robot operating system based replayer, we replay the data according to their timestamps to the other nodes, ROS nodes. And from the last ROS node, the data is sent via TCP-IP to ensure lossless streaming to the real-time PC, what is based on initial instruments and has a LabVIEW software running on it. And there we have the LabVIEW processor, which sends the data to a queue. That's the last queue here in the system, and that's why the playback buffer. And then the data, after a time, the data is streamed in real time to the device under test, depending on the interface on the application layer or the operating system layer by the driver, or directly on the hardware by FPGA. And yeah, at every process step, we take timestamps at the output and input of the process if feasible. And these inputs we use then later for input modeling and network calculus solutions. Here you see the chain described with the network calculus elements. The T0 is a timestamp in the measurement data. From that timestamp, we can generate a flow as bit over time and approximate the upper and lower arrival curve. From the output of the replayer, we grab a timestamp T1 and can also generate a flow of it and approximate the upper and lower bound. And the difference of the lower bounds of the output and input we use as a shift of the latency here. And we assume and sort also in measurements that we have then infinite service at this point. Then the data goes to the through the system as the processes I showed in the slide before, and every process we generate a rate latency curve with the measurements, and with concatenation we get the overall system service curve, and the output then goes to the playback buffer. And now the minimum needed delay or maximum delay in the system is between the upper input curve or U here and the overall system service curve. And at this point we shift the output. So the input is we assume, or we say the output of the system to the device under test should be the same as the input. That's why we can shift the upper and lower arrival curves to that point here and can generate the maximum, can calculate the maximum backlog size. Now to the arrival curve approximation, we assume that the mean rate is the rate for the token bucket curve, and the bucket we increase by iterative algorithm that increases the burst by 1 until the arrival curves doesn't cut the arrival flow anymore. And the latency parameter for the rate latency for the lower arrival curve is the found by the maximum deviation between the arrival flow from its mean rate. And the service curve approximation, in the first shot, we took the lowest measured latency we observed, so the observed worst case execution time in the system of the software processes, and used that for a rate curve with latency 0. And here you see results with a CAN stream on with different input rates. So here's the backlog, and here the delay, and with a rate of 4.2 milliseconds, what was nearly the lowest service rate here in the system. We can calculate the backlog, and it's compared to the simulation results. they are really close to each other. Then we put variation on the input, then the backlog delay, the backlog and delay bound both increase. But in the simulation, we found not such an amount of increase. So there is, it's a bit pessimistic here, the network calculus bound. And when increasing the rate, with this approximation, we cannot find any bound. It's an infinite bound. We need, when we want to operate the system in that mode, we need to use another approximation for the service if this is possible. And to the contribution, we used upper and lower bounds instead of the arrival flow, and showed it graphically, and also proved it mathematically and verified it by simulation in the paper. It's the first work of performance evaluation of a Hill system as a system under study. And as an advantage, the algebraic solution of the linear curves are fast and can be done with geometric calculations. The service curve approximation is okay until we reach the lowest service in the system. And the disadvantage I already said, when we want to operate the Hill system higher than the lowest service rate we found, then we need to adapt the service curve approximations. And now I did some further work on the approximation methods. Here you see the measured latency as a cumulative sum of messages over time in blue, and I approximate here the magenta one is the first method we proposed, so the worst case rate we found, and that's the curve here. Then a second method, we said, okay, we can think about to let the system work with the mean rate, and then shift the curve as far as they don't cut don't cut the flow anymore, like for the approximation for the arrival curves. And the third approach is to make a decent sorting of the data, create a new measurement curve, and then look at the rate of interest for the depending on the input rate, and then put the tangent here and create a rate latency curve based on that. Here is the easy implementation then for the solution with the RTC toolbox with the upper bounds, the service, and then the calculated delay, and then the shifted output curves and the buffer size. And here are some results of with the same input parameter of the rates and the different methods for when we are at the edge of the system service rate. The third and first method bring the same results as expected, because we put the rate at the same point, and the service curves are the same. Then for the second method, we have a slight higher calculated bound, but when we increase now the rates, we derive with the second and third method the bounds. With the second, they are compared to the simulation results, really pessimistic. I mean, we have now some bound. They are not infinite, but seem to be pessimistic. And the third method is even more pessimistic. But depending on the on the data size of the packets. Like in CAN, we have just some bytes. These bounds can be used in practice to calculate bounds on the RAM size and so on. So there, in practice, there may be no, we may not improve it more. It's depending then on the data size. And yeah, what is left for future work is scaling the system up to multiple parallel streams. We already developed our discrete event simulation model. We developed a scheduler there, and then we need to propose network calculus solutions for the parallel streams scheduled on the CPU cores. I had a look in the real-time calculus toolbox, the MPA approach, but that's more for hard real-time systems. And yeah, here we have a soft real-time system. And what we else wanna do is to use the network calculus solutions, the KPIs as KPIs for our health monitoring framework in the context of observability of our systems when they run in a hill farm, and there are running multiple of them, that we can do performance tests all the time, and calculate some risk of having overflows of in our RAM drives or at the last buffer, and also calculate the minimum needed delay to pre-buffer the data. That can also decrease the buffer size at the end. Yeah, thank you for your attention, and please feel free to ask questions or discuss it or give hints.
Okay, we probably turn this. Okay, can you hear us?
Yes, I can hear you.
So, any questions from the round? All right, so I actually have one question concerning the traffic patterns in this system, or in this hill system at the beginning, on the one of the very first pages that you had. So maybe we can go to, I think it was slide 2 or something. Yeah, no, yeah, one more, yes. So I was a little bit intrigued when you were speaking of the output of ROS, or the traffic generated by ROS, because I know from experience that it's a little bit hard to model. So I was wondering, the arrival curves that you assume here, how do you obtain them?
You mean the curve based on T0, or the output of the replayer? So
the output of the replayer. Let's start with this.
Okay, yeah. So yeah, we performed measurements, and we found out that the replayer behaves like a token bucket server. So it seems to save the data for 100 milliseconds and then pushes out the data with the input rate afterwards. So we have a really a burst rate curve, and in the replayer, there's a own written code that looks on the original timestamps and tries to replay them, but with a little bit of jitter. So that's why I also draw these upper bounds and lower bounds higher than the input, because we get some jitter in the system from the replayer itself.
Okay. Thanks. So any more questions from the round? If not, then let's thank the speaker again. We move to the next talk, which is also yes. So the next talk will be given by Raphael Ispo. He's